Hello, everyone. First of all, thank you to the organizers for inviting me to this online conference to give a keynote talk. My name is Bismark Singh. I am an associate professor at the University of Southampton in the UK. Let me share my slides and my presentation now. Okay, so as you see, the title of my talk is A New Data-Driven Framework for Balancing User Accessibility and Facility Load Fairness. So this work is a collection of a series of works that I have been doing primarily with my students over the last several years. And this will be a summary of these topics and the results that we have achieved. At the end of the presentation, I will also provide you with a list of the publications that have resulted from this work. Okay, so let me begin with a motivation of this topic. The motivation of this topic comes from combinatorial optimization problems of undesirable facility location. So these are facilities such as waste management centers, recycling depots, or landfills, even sometimes airports, which provide essential services, but at the same time, they have some externalities which are negative. For instance, they impose a burden, whether that's environmental or social or economic, on the populations that reside around these facilities. So the issue becomes when we have to determine which are the facilities that are to remain open or which are the facilities that may be closed, we want to serve two seemingly conflicting goals. The first is the access to these facilities because they do serve a purpose that is due to the essential characteristic of these facilities. So we would like to have a high user accessibility of the residents throughout a region. At the same time, we would also like to ensure the load that is placed on these facilities, or rather the communities that live around these facilities, is fair in some sense. So we do not know yet what fairness precisely means in this context, and that would be the mathematical question that we would like to delve into in this talk. What does fairness mean in such a context? To answer that, we introduce a problem that we call as the balanced facility location problem. That will be the crux of this talk. As an illustration, let us consider the state of Bavaria, which is the largest state in Germany. So this state has of the order of 2,000 zip codes, and there are about 1,400 of these which have a recycling facility in them, at least one recycling facility in them. We have the population UI for each of these zip codes from the census, and we have the capacity, which is estimated as a function of the catchment size of the recycling centers for each of the locations J. Then we have a mapping data between every facility and every user that we term as PIJ, which determines the preference of the users residing in zip code I to go to the facility in zip code J. This preference decays with distance. As the distance between I and J increases, the preference of I to J decreases, simply because you are less likely to go to a facility that is farther away from you. This heat map up here denotes the colors up here denote the access to the different facilities, which is coming from the PIJ. So for instance, you can see in this region where there are no facilities available, the facilities are given by the black dots. I'm sorry. So the facilities are given by the black dots. So these facilities do not have communities around them, and hence the colors are darker to begin with. So because the population has to travel a larger distance to go to them. We will come to this in great detail throughout the work, but this will serve as a test case for us for our analysis. One of the first things that we did was to empirically determine the Pij function. So using a survey data that was conducted in Germany a few years ago, we determined the probability of moving from one location to another as a function of the distance t. And we used what is pretty standard in the spatial geography literature, a decaying function that determines the probability of traveling at least d kilometers away from you. So this is an exponential decay, which models the mobility of the people. So this is the result that we found. So here is an empirical fit differently for both the urban and the rural regions. If you are living 0 kilometers away from a facility, so that means if D is 0, then you have a perfect amount of willingness to travel to that facility, and hence the fraction of people traveling is exactly 1. And you would see that this function decays strongly over the distance, which is reflecting the preference of going from one facility, from one zip code to another in which a facility resides. But all this serves as data into the models that we will build. So let's go on to some of the mathematical models related to optimization that we will study in this presentation. So here is the balanced facility location problem that we introduce. So it is a facility location problem in which there are two decision variables, x and y. The decision variable y, indexed by j, determines whether a facility is opened or not. The decision variable x, which is indexed by I and j, determines whether users from region I are assigned to facility j or not. Such a mapping can only take place if the facility is open. That's determined by this constraint. And we would like all the users to be assigned to a facility. So this unique assignment constraint ensures that every user is assigned to one and exactly one facility. We have a budget of how many zip codes from the total of j to select, for which there would be some mappings conducted. This budget is enforced by this following knapsack type constraint. We have the capacity of each facility, J, the capacity is C of J, and we would like that capacities are not violated. In other words, the amount of residents moving into a particular facility from throughout all of the available zip codes, so that's this numerator up here, better be less than the C of J. If we scale this in terms of a ratio, we could equivalently define an auxiliary variable U of J, which is the utilization of a facility, and we would hence term that this utilization is less than 1. The numerator up here, once again, is given by the product of three terms. Ui is the population of zip code I. Pij is the preference of moving from I to j. Hence, ui times Pij determines the amount of residents moving from I to j. Multiply this with xi of j, which is either 0 or 1, tells you in reality, is there such a movement or not? You sum this over all the i's, and it gives you the total amount of inflow into j. So these constraints are pretty standard for facility location problems, such as the p-median problem or such as the capacitated facility location problem. The objective up here is a quadratic term which takes the following form. So we have 1 minus u of j denoting the idleness or the emptiness of a facility j, and that term square is being minimized. In other words, we would like to ensure that the facilities are used high enough. So we would like to ensure a little amount of the idleness in each facility. This term is scaled by the capacity of the facility C of j, meaning we are incentivizing low idleness in large facilities. And we penalize these deviations strongly due to this square up here. So this term is a quadratic, yet this term is a quadratic uh, penalization term subject to linear constraints due to the binary variables up here. So this has a non-convex optimization structure. The claim is that the goal of this optimization model is to balance the utilization across the open facilities, and it would ensure some meaning of fairness and at the same time a good amount of access. Now we would see how this claim is justified. So as I already mentioned, here is the interpretation of the model. One thing to keep in mind is the following intuition that hasn't been formalized yet. So this quadratic objective, it is seeking to generalize both an access maximization structure as well as a burden balancing structure. So these are two goals, and they are probably conflicting to each other in most instances. The standard way is to model these with a multi-objective or a bi-objective structure, where both of these goals are being optimized for. However, we claim that in the following model, which is relatively clean, you can achieve both of these goals simultaneously with a single objective. To do so, we have to define what does fairness mean in this context. The classical facility location problems study fairness from the perspective of a user, where fairness is defined in terms of large amounts of accessibility or an equal amount of accessibility, or accessibility being in certain pockets or radius from the user. But in contrast to this, we view fairness from the perspective of the facility or from the communities that live around these facilities. So once again, let's get to this small u of j term, which is the utilization. So the notion is that we would like to utilize these facilities in an equitable or comparable fashion. But if we do so completely, then this would disregard the preferences of the users. For instance, some users might be assigned to facilities that are very far from them, in a goal to maintain equal utilization throughout the state or the region, which would not serve our purpose for accessibility. So the question is that how could we create an axiom of fairness in a way which fulfills both of these perspectives? So here are two fairness axioms that we propose. So let us compare two facilities J and J prime. Compared to a single user I, the preference of I going to J is larger than that of I going to J prime. In other words, I prefers J. In an optimal solution, if I is indeed assigned to J, then there is no reason for a complaint. Such a fairness, if it happens for all the user pairs J and J prime, is known as a warranted fairness. It's a notion that we propose. In contrast, if warranted fairness does not hold, then we have a user who is assigned to a facility that the user did not really prefer. So, in other words, I is assigned to J, which was not preferred by I. So to make the facility J, to provide some compensation to the facility J, which is being allocated users which are not compatible to this particular facility, we would say that let us compensate you by providing you with a lesser amount of utilization than the other facility. So to make this formal, if there is a facility that is receiving some users who are not preferred by this facility, then that facility better be utilized less. So if that happens in an optimal solution, then we would call that fairness as a compensatory fairness. So a full fair allocation will be one in which an optimal solution for all ordered pairs J and J prime satisfies either warranted or compensatory fairness. In contrast, there is a notion of proportional fairness, which is very pervasive in the literature as well. So this comes up frequently in networks, in electrical engineering, and several other computer science implications as well. In its most simplest form, proportional fairness, as is in our setting, would mean that all facilities which are open have the same amount of utilization. So this is the utopian notion of fairness. In a previous work, we have studied such a notion of fairness in great detail. So if all the facilities achieve the same amount of utilization, we will call this as a proportional fairness. So the question is, what type of fairness allocations are achieved in our optimization model? So let us take this very simple example, which is constructed to illustrate a point. So there are two users with the number of population being 10 and 10, and there are two facilities with capacities of 8 and 16. The preferences for both the users to both the facilities are marked with these arrows. And the only feasible solution that we have up here is to assign the first user to assign the first user to the second facility, because the first user cannot be assigned to the first facility because the capacity is only 8. It requires at least 10 times 0.9, which is 9 amount of users to go here. So the first user is assigned to the second facility, and in the same way, the second user is assigned to the first facility, both of which are unpreferred by the users. Since the amount of utilizations are not equal, so this notion is of course not proportionally fair. It's not warranted fair because we are assigning users to their unpreferred facilities. It's also not compensatory fair because the first facility where the second user is being forced to be assigned is actually being utilized more than the second facility. So this notion, in this small instance, the notion of fairness is absolutely not satisfied, not even in an optimal solution, but even in a feasible solution. So what could we do, and why did we seek such a model? So we say that if you relax this model slightly, that is, you replace the binary restrictions by a continuous relaxation of x being between 0 and 1, but you allow the y to remain binary. Then you could prove through the KKT conditions, the necessary KKT conditions of this optimization model, that the optimal solution does indeed achieve a fair allocation. The proof comes from the KKT conditions, as I said. In a special case where you additionally enforce that the preferences have been completely removed, so the Pij is independent of I, and you still allow the binary y's to remain, the x is continued to be relaxed, you can show that the optimal solution is also proportionally fair. So this structure completely breaks down into a very special notion of proportionally fair results. Again, the proof is from the KKT conditions of this. Let's go further and study the theoretical complexity of this model. So let's recall what this problem is. So we have a quadratic facility location problem, similar to a quadratic assignment problem, but the objective is seeking to balance this utilization and accessibility. By now, it is more clear why we have this special structure of the objective and how it is seeking to balance the two conflicting goals. So let us consider a subproblem of this main problem. So let's say that you have already fixed a set of facilities to open. So some subset S of J is already open. So then the y variables have already been determined, and we are left with simply an assignment problem in a way that minimizes the objective function. So this objective function is the same as before, 1 minus u, which is the utilization, with the constraints now being only over x. So that means we only need to construct an assignment for a given set of open facilities. However, even the feasibility of this assignment problem, so that means that if you don't have any objective, so even that problem is NP complete. So this is an older result. So this is simply a user assignment problem. So this result is known from the literature of the facility location problems. But what happens if you enforce the objective function within it? So we have shown that in the absence of an objective function, so this sub problem is hard. With an objective function, so what happens? So you could simply say that if the capacities of the facilities are large enough, then you could map any user to any facility and get a feasible solution. Indeed, that is right. However, in the presence of an objective function, even if you have sufficient capacity, then this problem remains hard. And you can show this by reduction from the partition problem. So the problem is NP hard. Recall that this is not the main problem that we are studying, but this is the sub problem that we have shown is hard. So since the sub problem is combinatorially hard as well, so we were motivated to study further structural properties and relaxations of this problem. Let us look at some of the structural properties of this model. So once again, we could take this notion of the sub problem, and let us try to look at this. So, but instead of looking at this as an optimization model, let us look at this as a part of a set function. So where the function is that of the facilities S, which is a subset of the facilities J that are available to be opened or not. So let this function f of s. Let us define this function f of s as seeking to minimize the objective function that we had earlier. So this is nothing but the same objective function, which is now split into the set of open or selected facilities S and the unselected facilities which do not belong to S. So for the unselected facilities, the term X is 0, and hence the term in the subtraction disappears. The set to be optimized over calligraphic X is the following polytope that we have seen earlier. So our goal up here is now to characterize the structure of the subproblem F. And how does this F fit into the main real problem that we are solving? So that is simply a cardinality constraint minimization problem, where we are minimizing f of x subject to a cardinality constraint. So some of the results that we have shown already are that this f is sub-additive. It is also monotone and non-increasing. But this is a main result. It fails both in submodularity as well as in supermodularity. So, although proving the lack of submodularity was easy, but the lack of a structure of supermodularity was quite involved. So it took us some effort to prove this this result. So we did this by constructing counterexamples for both the capacity regimes of sufficient as well as insufficient capacity. The reason we started exploring this was that we were getting results that were nested in practice. But we then showed that this does not lead to the supermodular structure, and hence it enforced that there is some type of a structural fragility in this model. So I will leave these slides with you, with the organizers, and I will just go to the last result up here to the conclusions in the interest of time. So let us conclude by seeing the summary of this problem. So we studied a problem that has a combinatorial core structure, which is NP complete. It resembles this assignment type of a problem. However, in the general case, it remains neither submodular and nor supermodular. It enforces some notion of this structural fragility coming up here. What I didn't talk about today is the curvature of this problem, which remains bounded and which measures how much are you deviating from modularity. Then there were other results which are not talked about. However, they are in the papers which have resulted from this work. So this work has led to a series of publications. The two of these are in the Informs Journal on Computing. There is an applied work that was published in Networks, and we have a work that is already in review. With this, I will stop here, and if there will be any questions, I will be happy to answer them.